Okay, so the first kind of export that you might want to do, you've made a picture. You might want to, whether it's being of this level or the sample clustering, you want to show your supervisor or whoever it is. And so what you can do is render it to file. Okay, so this will take your screen and make a screenshot of it and put it on the desktop. It'll generally try and give you a thing, and it'll go there, and there's a picture. If you want to make a high resolution version of that for publication, which is a bigger file, just do that again and it'll save it as a high. And it may take some time. That'll make a really nice picture. And it looks like it's such a nice picture, it's taking ages. I think I know why. So that's a really high-res picture where you've got it there. And in rendering, yeah, so this figure here will make it 5 times bigger. So I generally use that as 2, and that's big enough for all publication. And that will be a lot faster now. And the file will be a lot smaller. Done. Okay. First thing out is a nice picture that you want to generate, and obviously going over to 2D sometimes you can make a nice picture, you can move things around, you make it nice and pretty, and you'll go on and annotate that later. Okay, going back to this, so let's say I've got all of this data and I'm quite happy with it. So what you can do, so the other thing is to save this file. So if I save this file, save graph as, okay, and a layout file, I'll put that on desktop. Okay, so it told me there that I'm going to save this layout file in a separate folder from the expression files, and I'm going to resave that now, and I'm going to put it into the sample data with the gene expression, so that it actually is saved. So you might want to save that. So the things you want to remember about a graph is what the correlation value was that you used to create it. So I'm going to make that 0.9 because that was what we're here. And then I might want to say MCL 2.2. Yeah. So that's the the value which I've used to actually cluster it, and I can save that there. Now the thing about that is that when I come back to this now, there's this layout file, and if I drop that layout file here, he says, get back. Okay. So a layout file is different from the input file because it stores where everything is. So it'll be identical to the graph you've just been working on. If you reload the data from the start, then you may find you should produce exactly the same graph, but it may look slightly different because the layout algorithm is a random generator and it will work out what is best. So if you save a layout file, it's exactly the graph, and it saves you on the time and effort of redoing it. It'll save your clusterings, it'll save the work that you did on it, so it'll be an exact copy of what you were working on. Okay, and if you need to save it in with the expression file, so that when you come into here, you can actually get the expression values associated with it, because if you don't save it with the expression file, then it doesn't have the numbers behind the graph. Does that make sense? You don't get the expression values because it's just a graph. In fact, can I load it in? Does it let me do it? Probably not. I want to see if it'll let me in. Okay. So just to say something about the structure of a layout file, what it stores is the relationships. So now we have a probe, so it doesn't have the expression data in it at all. It just stores probe set, how they're related. And if we go, they're big files. When we get down to the bottom, it has node class. So a node class are all the bits of information that we had associated with nodes. It'll store the color, it'll store the position of a node. So all of this is kind of what's in a layout file that isn't within the input format, you know. So it doesn't have to lay it out again. It knows what color, shape, size nodes are, and it'll produce that exactly back again. Okay. So a layout file is your record. It makes it quicker and easier to load the last data set to give you an identical copy. If you then, so I've done my analysis, and I decide that these guys here are not interesting to me. I want to get rid of those because that's just technical noise I've just deleted, and I only want this bit here. Then there's two things I can do. I can then say save graph as, no, that's not the one I want to do. I can then say file, save visible graph. So visible graph is only save the things that I'm looking at now. So even though I might have sort of hidden unclassified nodes, or I might have hidden that bunch of nodes there, when you save the graph it'll still be saved because they're still in memory. If you say visible graph, then you're only saying what's on screen. So you're kind of hiding things that you have now got rid of. Okay? And we can say visible graph. Okay. So there's a way that you can go through and filter through data. The other way I can now do this, and probably the most useful way of outputting all of your data. So I'm selecting all, so I've decided that this is the meaning of life of my experiments, that I've got rid of all the stuff that isn't interesting. And there's a number of different ways you can get rid of interesting stuff. You can get rid of low intensity data. So data which is, never gets above about 100 in any of the experiments. I don't really trust that stuff anyway. You can either filter it off in advance, or you can filter it off before some other level, and you end up with these are all the things that I'm interested in. So when I plot that now, I've got each profile of every cluster within that graph. I've got all this information here, and basically then I can export table. Okay. So this is probably the most useful way of exporting data. And what you'll end up with is a tab delimited file, which will have all that information that was in that table that you just saved. Okay? It doesn't have the expression data. It just lists that these set of genes are in that cluster and these things are grouping together. So this is your cluster defined set of interests. That's where you can then take this set of genes and then go and say, what's the Go enrichment in them? Is there a pathway enriched in them? All that kind of interpretive stuff that you might want to do with that set of genes, you can do from that point onwards, okay? Because that's the list. So rather, what it doesn't have is a p-value. You know, that might make some people uncomfortable, but the reality is there's a kind of, as I say, there's a statistical improbability that these things are going to be together. After looking at hundreds of data sets, I can tell you that if the experiment was good, you'll get a great biological enrichment within that. Okay. The other thing to mention about just looking at data in this way, you want to use all your data. You don't want to sort of average out your replicates, because if you have got a set of dodgy replicates, you will see it obviously. So generally when I'm looking at a replicate, so Claire with her time course, how many time points do you have?
4.
4 time points.
3 rats.
3 rats.
2 replicates.
Okay, so I would want to take each rat and show it as a separate group, 0, 2, 4, 7, 24, 0, 2, 4, 24, so that if one of the rats, once you start looking at individual animals, they respond differently. And it's kind of useful to see that. When you start grouping everything together and say they're all the same, they're not all the same. And quite often what you want to do is see how variable they are. And obviously inbred rats or inbred mice tend to be a lot variable than humans, but certainly looking at bone marrow derived, blood derived human monocytes, they're different. We know they're different. They respond different to TNF. So it's useful to be able to see that. A lot of methods basically collapse everything down and you never see that. The thing I like about this tool is I can actually see my data. I can see where the replicates are and I can use that replicates to plot. So even if only 2 of them worked, I know that there's a Duff replicate in there. It didn't work, that replicate. I know that, and I understand that the 2 on the other side work beautifully and replicated, and I can possibly consider saying I only ran 2 replicates because I know one of them didn't work. So it's very useful to look at that raw data and to understand how replicates are working and to look at that primary data. As I said, you can do a lot of things within here. There is, let's just go back to one cluster. Just in terms of looking at that, you can put on the standard deviation, but standard deviation is fairly meaningless when we're talking about gene expression data, because essentially I think we can do a plot like that for whatever, and generally mean is fine. I think there's a median now. There is a scaling. So some people like to use various scaling methods, so you'll see that all the numbers have changed here. It's the same data, median centered, doesn't mean a lot in this case, unit variance. So these are all, in this kind of data it doesn't matter too much. If we'd looked at time course data it would look different. There are various things you can look at there. There's things you can do in here in terms of changing the properties of the graph, changing plot background, changing the axes. So it's actually quite enabled, this graph now. You can change a lot of different things about its appearance, and you should be able to generate publication ready quality graphs from here. Now one thing that this version doesn't have, which is a slight problem, we've changed it since then, that you can actually, in the later versions of this tool, those class sets that you put in about your samples that said that this is replicate 1, this is replicate 2, this is replicate 3, you can display these under here, okay, so that you can actually have these blocks and you can begin to see that. So what you're going to be doing is, when you're looking at data, is you're pattern staring. You're going, how do I understand this? You're trying to relate what it is that you thought you'd done relative to the patterns of data that you see before you. Okay, that's generally, you've got to believe your data after all, and that allows you to do that.